Hello, everyone, and welcome back. My name is Mr. Cobalt, and in this video, I'm going to talk to you about how to predict the types of radioactive decay given some isotopes. So here, I'm going to go over some practice problems. So in these practice problems, we're asked to predict whether or not the nuclide is going to most likely undergo decay via the beta decay or positron emission. So here we have a list of nuclides to figure out whether they're going to undergo beta decay or positron emission. So the first thing you're going to want to do is figure out the ratio of neutrons to protons, right? So here I have my island or band of stability or my valley of stability here, and I'm going to use this and the ratio of the neutrons to protons. And so if your isotope or nuclide has the proper number of the proper ratio of neutrons to protons, then it's going to be stable. If it doesn't have that ratio, if it's too high or too low, it's going to undergo a decay. And which decay it undergoes depends on if you've got too high of a ratio and you need to bring it down, or if you have too low of a ratio and you need to bring it up. And so it all has to do with the number of protons versus the number of neutrons. And so this is what the band or valley of stability tells us. And we can also use the molar mass or the atomic mass of the elements as well, because that gives us a natural weighted average of the isotopes of each element. So if we see that, say, for example, the mass of this isotope is either too large or larger than the weighted average that you find on your periodic table, or if it's lower than the weighted average you find on your periodic table, that will also tell you what kind of decay it's most likely going to go through. And the decay it's going to go through is going to be that decay that which is going to bring it closer to that average or bring it closer to that neutron to proton ratio. Okay, so let's get into this. So we have magnesium 28. So we need to figure out how many protons and neutrons this thing has. So it's the mass number is 28, which is the number of protons and neutrons together. So we look on our periodic table for the atomic number of magnesium, and that is 12. So it has a atomic number of 12. And so if we subtract 12 from 28, that's going to give us 16. So that means we have 16 neutrons and 12 protons. And so if we find the ratio of that, we find that it is 1.33. Now, that's the ratio we have. And this is our band of stability. So let me take this off and bring it closer. So here you could see in the band of stability, here we have the atomic number Z. Here, up here, we have the neutrons, N, the number of neutrons here on end. So here we have the neutrons, and here we have the proton number. So magnesium, as we said, has a number of protons, 12. So that's going to be over in this area here. So you could see here that the ratio that is going to be stable for these lighter elements is more like 1. So 1-to-1 ratio. But we have for our element a 1.33 ratio. So that tells us that the ratio is too big, right? So if the ratio is too big, if the ratio is too big, then that means we have too many neutrons and not enough protons. So this is going to decay in such a way that it's going to lower the number of neutrons and increase the number of protons. So we need a decay process that causes neutrons to go down and protons to go up. Well, that would fit with the beta decay. So beta decay is where you are losing a negative electron, right? And so this negative electron, this beta particle, is produced when you have a neutron that's breaking up into a proton and electron. And the electron, the beta particle, is released from the nucleus, and you're left with a proton. So one neutron disappears and becomes a proton. So you're lowering the number of neutrons and you increase the number of protons through beta decay. So this one's most likely going to undergo beta decay. This funny looking B is the Greek symbol beta, so beta decay. You could also look at the periodic table at the atomic mass. So if you look at the atomic mass of magnesium, and magnesium has an atomic mass of 24.31. 24.31 is the average mass of all the naturally occurring isotopes for magnesium. So you look at this particular isotope, it's a 28. That's larger than the weighted average. So again, it's too big. So we need to decrease the mass by going through beta decay, right? So we lower that mass. So that's another way that you can understand it as well. Okay, so what about magnesium 22? So we do the same thing. So we have 22. This is our protons and neutrons. So we need to subtract out the neutrons, subtract out the protons. So that means if we subtract out 12 again, we have 12 protons again. So minus 12, that's going to give us 10. And now we have 12 here. So neutrons on the top, protons on the bottom. So our N to P ratio is then going to be 0.83 now. So now, as we said before, the ratio for a stable isotope that's not going to undergo any decay is more closer to 1. So it's a 1-to-1 ratio. So here our ratio is too small. And so here, this means that we have too many protons and not enough neutrons. So we need to decrease the protons and increase the neutrons, and that occurs through positron emission. So just to be clear here, beta decay is where you are going to have a neutron and convert it into a positive proton, neutral neutron. And in the process, an electron or beta particle is released, right, out of the nucleus. So here we're going to have positron emission. And in this case, it's the opposite. A proton becomes a neutron. And this, I should probably draw it the other way. And in the process, a positron or a positive electron gets released. Sorry about that. So this is more likely to undergo positron emission. And again, we can compare the mass of our particular magnesium nuclide isotope and compare that to the average, the mass weighted average on your periodic table, which is again 24.31. And again, 22 is less than 24, so this is a lighter isotope, so it's too light. So it's most likely going to undergo positron emission for the same reasons. Okay, so what about molybdenum 102? Same thing here. So we have 102. We need to look up the atomic number of molybdenum, and that is, where are you, MO? MO, where are you? There you are, 42. So number 42 is the atomic number, so that's 42 protons. So we're going to subtract 42 from 100. That gives us 60 neutrons left over and 42 protons on the bottom. So we do our ratio here, and the ratio here is 1.53. Once again, oops, not 5.3, 4.3. So we have 4.3 here. And once again, we look at the ratio here. And so here's our valley of stability. And so now we're looking at an element that's 42. So it's about here in the atomic number. So if you go up to the line here, so that's around 1.27. So this isotope of molybdenum should be around 1.3, right? But we have not 1.3, but 1.4. What was it? 1.43, right? So the ratio here is too large. So once again, because the ratio is too large, just like it was too large here, we would expect we need the neutrons to decrease and the protons to increase. So we need neutrons to go to protons, and so again, we're going to have beta decay. So we would expect beta decay, for this isotope of molybdenum. Okay. What about lead 192? Again, same thing. We got to look up lead. What's the period? Get your periodic table. Look up lead. The atomic number of lead is 82. So here, 192. We're going to subtract out 82. And when we do that, we get 110 for the number of neutrons and 82 protons. That's an ugly P. So we got protons there. And so if we calculate this ratio, let me calculate the ratio really quick. 110 divided by 82 equals, we get 1.34. 1.34 for the ratio. And if we look on our valley of stability again, right, we see here 82 is over here. You go up, and we're up here. And so you can see that the ratio should be about 1.5, right? So that would be stable. But here we get 1.34. So this is too low compared to the average, compared to where it should be on the valley of stability. So in that case, we need to increase the number of neutrons and decrease the number of protons. So again, we need to get rid of protons. So we need a proton to become a neutron. So again, this would be positron emission. And again, you could look at the average mass on the periodic table. So if you look up lead on the periodic table, the weighted average atomic mass of your lead is 207.20. 207.20. So this 192 is smaller than that. It's lighter than that. This atom is too light. So we need to change that. So we're going to increase this ratio. So you can do that. Same thing with molybdenum. I didn't do that for molybdenum. So the average atomic mass of your molybdenum is 95, 94. And again, you can see here 102 is much greater than that average. So you want to, it's too heavy of an isotope, so you need to decrease the mass of it. So next is lead 212. Now you can see here that we have a heavier isotope of lead. So we're going to expect the ratio to be higher this time around. So we're going to remove 82 again. So here we went from 192 to 212. So we gained 20 particles. So that means we've gained 20 neutrons. So this is going to be 130 neutrons, and still we have 82 protons. So now you calculate this and you get 1.58, I believe is what the calculation is. And so now we said that it should be about 1.5. This is 1.58. It's a bit heavier than you would expect. The ratio's a bit higher than you want. And so again, that means that we have too many neutrons, not enough protons. So we need a neutron. We need to lose neutrons and gain protons. Well, that happens in beta decay. We lose a proton and it becomes, lose a neutron and becomes a proton. So this is most likely to undergo beta decay again. Okay. And again, 212 is higher than the average atomic mass that you find on the periodic table for lead, the weighted average. Again, the weighted average, I think, was 207. So this is bigger than 207. So we want this isotope to get smaller, right? Okay. Now here, xenon 114, right? So xenon 114, we need to look up the atomic number of xenon. The atomic number of xenon is 54. 54, let me double check that. Yes, 54. So we're going to subtract 54 from this 114. 1014 is the neutrons and protons. We're going to subtract out 54 of the protons, and that's going to leave us the neutrons. And so we get 60. So we get 60 neutrons left over, and we're going to have 54 protons. And when you calculate the ratio, you get, so let's say 60 divided by 54 equals, you get 1.11. And if we look on our valley of stability for 54, so you could see here 54 is in between 40 and 60, so it's pretty much in the middle. You go up the middle here, keep going up the middle, and we're around here. So the ratio of neutrons to protons should be about 1.3, maybe a little bit more than 1.3, maybe 1.35, right? So that means that the ratio that we have here, 1.11, is too low. So meaning we don't have enough neutrons and we have too many protons. So we need protons to become neutrons. We need to increase neutrons, decrease protons. And again, that's going to happen with positron emission. So positron emission is most likely going to happen. So again, remember, positron emission is where protons become neutrons and it releases a positron. So emits a positron. So in the process of the proton becoming a neutron. So the proton, if that happens, the number of protons will decrease, the number of neutrons will increase, thus increasing this ratio. And if we look at the atomic mass of xenon, it's about 131. So the weighted average atomic mass of xenon is 131. You can see that this is a smaller isotope. It's too light. And so from that, you want it to get bigger. So you're going to have to add neutrons, right? So add neutrons to this. Okay. Um, so that's it for this. I hope this was helpful. If you found this helpful in any way, and if you enjoyed this video, then please, by all means, like the video. Hit that like button over there somewhere. Share the video with your friends. Make sure you subscribe to my channel. Hit that notification bell. And when you do, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me and have a great day.